All right, great. We're going to open up the afternoon session. And our first speaker is Ming Wu. He's a Nortel distinguished professor of electrical engineering here at Berkeley, not just the Nortel professor. And he's co-director of the Berkeley Sensor and Actuator Center, and also faculty director of the Marvell Nano Lab here. Like some of us here, he's an AT&T Bell Labs refugee, hiding out in these various universities. So he stopped by UCLA for a while, just like Eli, and then came here to Berkeley. So without any further ado here, he's going to tell us today about his work on nanophotonic devices for energy-efficient optical interconnects.
Thank you, Gene. It all sounds like a conspiracy. This is first of two talks that will focus on interconnect, and Professor Stoyanovich will talk about a lot of interesting work about integration with CMOS process. Here I'll focus more on the sort of fundamental aspect. How does the energy scale with photonic devices, and how can we achieve low energy, and what does that require? So before I start, I'd like to acknowledge the students and postdocs who did most of the work. My nanophotonics team includes Amit Lakhani, Michael Eggleston, Ryan Goen, Taejong Sok, and postdoc Myung-Ki Kim, and two former postdocs, Kyung-Sek Yu and Owen Lau. And I also like to thank our collaborators in the nano LED projects. We're working very closely with Professor Yablanovich's group, Nano Laser with Connie Chang-Hasnai's group, and on the detector, we've been working with Ilet Alon. And I'd like to thank our sponsors as well. So this is the outline. I will go over a very brief introduction, focusing on the trade-off between energy and sensitivity, and show that how nanophotonic devices provide a key to address these fundamental trade-off issues. And then I'll summarize my talk. So I think now we don't need much convincing that the interconnect is becoming a very serious problem in the overall energy consumption in chips and microprocessors. It has exceeded much more than 50% and is on the rise to perhaps greater than 80%. If we look at the current energy that's being consumed for short-distance communications, this includes both on-chip and off-chip. And for off-chip, it consumes on the order of picojoule per bit. On-chip is usually 100 femtojoules per bit or less. And as the chip scales up, I think Stoyanovich will provide much more concrete examples that there's increasing demand of bandwidth that cannot be met with electrical interconnect, as well as the energy consumption. So optical interconnect provide potential to not only increasing the bandwidth capability, but also lowering the energy consumptions. So let's look at how much energy it takes to communicate over short distances. So there are several different aspects to this. Let's look at first the fundamental aspect, that is the quantum limit. This is because the photon or electrons are discrete quanta, and there is a statistical event. In order to ensure sufficiently high link quality, measured in terms of bit error rate, let's say pick a bit error rate of 10 to the minus 15. The Poisson statistics that photon follows requires at least 17 photons per bit on the average to achieve this kind of low bit error rate. Now, there is two issues involved in designing a link. There is energy issues, how, for example, measured by joule per bit, And there's a sensitivity issues. How many photons do you need in order to successfully complete the link? And if we look at the current commercially available link that are carried by photons, for short distance, let's call this interconnect, it operates at 10 to the 5th photons per bit, so 10,000 times more than what we need for quantum limit. It's consuming roughly about a picojoule per bit. For long haul, when we send information across the continents, across the country, the energy consumption is not as big a problem, but the reach is more an issue. So higher sensitivity usually is being favored at the expense of higher energy response. So 10,000 photons, still about 1,000 times higher than the quantum limit. The energy consumption can be explained by a very simple circuit model. Here we have the energy versus sensitivity. And the energy consists of two parts. One is the energy carried by the photons itself. So it's linearly proportional to the number of photons per bit. And the more number of photons, the larger the electrical signal that's recovered by photodetector. Less work is required for the amplifier to boost up the voltage level. So the amplifier energy consumption actually goes down. So these two forms a fundamental trade-off. And you can see that the sum of the two, the minimum energy consumption shown here by the green dot, roughly coincides with these 100,000 photons per bit at about 1 picojoule per bit. And the long-haul communication, the trade-off is made such that we favor the sensitivity, but as a result, the energy consumption is actually higher. So here the question we like to answer is, in order for this technology to become eventually available on chip, we really need both high sensitivity and low energy at the same time. And therefore, we need to fundamentally break up this trade-off. So we are asking ourselves, is it possible to achieve nearly quantum limited detection, say approaching 20 photons per bit, at fundamental energy? Here by fundamental energy, I meant the energy carried by these 20 photons per bit, and not much beyond that. It's roughly about 10 attojoule per bit. Okay. So in other words, we like to move from this trade-off space from the green dots to the lower left corner, shown as the red dot. If we look at the simple model, circuit model for this link, generally the signal is generated by some kind of electronics circuits. It's driving an emitter. Light is being carried on a waveguide. Tremendous progress has been made in the area of silicon photonics. Silicon turns out to be a wonderful transparent material for photons in the infrared spectrum. Very low optical loss, so that's a primary advantage for carrying the signal over, say, distance comparable to the chip size. The energy recovered by a photodetector, which then, after some conditioning, amplification, will be driving the next state logic. So as mentioned before, there are two trade-offs. One is linearly proportional to the number of photons, and the other one is inversely proportional to. And the red star, for example, here represents the optimum energy. Here we have a family of curves. This family of curves represents different trade-offs when we scale the photodetector capacitances as well as low capacitances. Now we know that the capacitances can scale with devices. So if we can reduce the device size, this is just a parametric calculation. For example, if we artificially reduce this capacitance, we saw that the trade-off point moves to lower left corner, lower and lower energy as well as higher and higher sensitivity. And if we are able to, for example, achieve on the order of tens of attofarad, which is possible for devices on the order of tens of nanometer, in which case we indeed are in the ballpark of tens of photons per bit and tens of attojoule per bit. However, in doing this calculation, this is primarily the energy consumption of the receiver. Let's not forget about the transmitter. The transmitter, if we use a laser, any kind of laser, for example, if we use a very low energy laser that we only need to provide a bias current of 5 microamp, this is in fact quite a bit better than what's available today. But even with a 5 microamp bias current, DC bias current, this now provides a lower bound for the energy consumption. That's already translating to about femtojoule per bit. So in order to reach this red star, we also need to work on the transmitter. We need to shrink the size of a laser so that it can be operated more efficiently. Or, as I will show you later, that maybe we should altogether do away with laser and just work on fast LEDs. Okay? So now the rest of my talk will be looking at nanoscale emitters and nanoscale detectors. So first on nanolasers. In principle, to make a laser, we need optical cavity. Optical cavity, just like microwave cavity, you can essentially do that with a size roughly comparable to half wavelengths, as shown in this example here. However, for optical wave, if you shrink the semiconductor cavity down to that small size, it actually behaves like a very good antenna. In other words, the energy leaks out like this standard dipole antenna radiation pattern. It is indeed quite a good antenna with a radiation Q on the order of 8. This is not good for a laser. Okay. So we have learned in microwave frequency that we can build a higher quality factor cavity by using metal enclosures. So same thing here, metal is very effective in stopping the radiations, as shown here by the examples on the right-hand side, where we put this semiconductor emitter, presumably an optical gain material, enclose it in all 5 sides except the bottom side with metals, and you see that we can almost completely cut off all radiations. We can also tailor the design to have a various amount of light coupling to the outside world. So with this so-called metal optics optical cavity, we can progress to scale down the laser size. There are several such kind of metal dielectric cavity lasers that's been reported. I'll show you some comparison towards the end. Here I'll show you the laser device that's made by our group, Amit Lankani. Here he basically adopted the technology of a microwave patch antenna. This is at the nanoscale, so it's roughly about 1,000 times smaller in size, where the dielectric is now replaced by a semiconductor gain media. In the infrared wavelengths, we use indium gallium arsenide phosphide as the gain media. And the top gold cap together with a ground plane that forms optical cavity. The quality factor of the cavity is on the order of 100. And we will observe various electromagnetic modes, actually almost exactly the same as in the microwave counterparts. Except that now we have observed charges which is now oscillating at optical frequency rather than at microwave frequencies. And the lowest order mode is called electrical dipole mode, which is due to the charge oscillating on opposite end of the nano patch, and with majority of the energy confined in the center overlapping with the gain media. So this is sort of desirable for laser operation. If you change the size, the wavelength is a very sensitive function of the diameter. So this provides a way to provide, for example, multiple wavelengths, as we will hear in the next talk, that wavelength division multiplexing is a very powerful tool also for on-chip communications. And here I also put this picture side by side with the same scale bar with transistors. These are 4 45 nanometer transistors from Intel. So you see that the laser size is now approaching the size of a transistor, still a little bit bigger than transistor. Transistor is getting smaller as well. Nevertheless, they are now at least the same order of magnitude rather than hundreds of times of difference in size. Moving on to do electrical injection, the previous example is excited optically. We will need to do electrical interconnect to provide a current path. The interesting thing here is now the metal not only conducts current, it also conducts electromagnetic energy or optical waves. So we have to design the air bridge very carefully so that the light energy doesn't leak out along the metal path. And the simulation seems to confirm that. We are on our way to make these electrical injected lasers. Just to compare the size with some other sort of more traditional lasers that we are familiar with, the lasers all the way to the right-hand side is the laser I just shown you. It looks like a speckle of dust if you compare that with the current commercial lasers that's being used in computer mice, as well as short-distance fiber optic links. That is vertical cavity surface emitting lasers. So it's hundreds of times smaller in size. Now, I mentioned this threshold current that we need to provide to the laser. And if we are directly modulating the laser, we need to bias the laser typically at 5 times of this threshold current. And that's become a very significant energy consumption. So a few years ago, we started to be intrigued by the idea that perhaps we can use an LED, which does not need any population inversion, doesn't need to have a gain to overcome the cavity loss, and perhaps it can be a more efficient emitter at the nanoscale. We all know that also that spontaneous emission is a slow process. The spontaneous emission time is about nanosecond, limiting the modulation bandwidth to about 200 megahertz, which is now way too slow compared with the electronic systems. One way to explain why this process is so slow is to look at the spontaneous emission effective dipole length. So a very good model is that you can think of this spontaneous emission as a radiating dipole, and the typical radiating dipole has a length of about 0.4 nanometer for typical semiconductors. And they are not efficient radiator, as we all know. Efficient antenna needs to be length on the order of half wavelengths. Now, using nano structures, if we, for example, attach an antenna to this nano emitter, very much the same way we attach a cell phone antenna to a power amplifier, we can make the radiation become a lot more efficient, and potentially we can even make it go faster than a laser, stimulated emission than a laser, with potentially even stronger emission, meaning more light coming out from such emission. And Eli has performed some fundamental calculations show that the fundamental bandwidth is approaching hundreds of gigahertz or even terahertz. And more interestingly, since we don't need to bias it, it doesn't have a threshold. So we say the first photon is fast. Essentially, we don't need to bias the device at all. We can save a lot of standby powers. And this emitter, even though it is an incoherent light source temporarily, the emission pattern is controlled by this optical antenna, and it is actually spatially coherent. We can focus it back down to a very small detector, as I mentioned, which is important to reduce the receiver energy. So if we look at it a little bit more quantitatively, the bulk spontaneous emission is described by this expression. I'll just focusing on the dimensional factor here. It is proportional to square of this dipole length, inversely proportional to the cube of the wavelengths. So here you see why this spontaneous emission rate is so slow. The dipole length is roughly 1,000th of wavelengths. Now, if we attach an antenna to the structure, we change the emission rate. Now the emission rate is controlled by a few things. One is how well the antenna is coupled to the emitter and how well the antenna radiates. And fundamentally, we can show that the dimensional dependence is now, we still have these dipole dependence, but instead of wavelength cube, it's now inversely proportional to the square of D, which is the gap sizing between the antennas. So by contacting the emitter at the nanoscale, much less than 50 nanometer, ideally on the order of 10 nanometers, we can have, if you compare these two expressions, roughly 100 times increase in the efficiency, actually 10 to the 4, 10,000 times when D is about 1% of wavelengths. In addition, it's also enhanced by the quality factor of the antenna. So altogether, about 10 to 100,000 times of enhancement can be obtained. So this is all very exciting, except we all know that metal is also very lossy, and that will obviously have some impact on the efficiency of such a source. We can actually analyze this. The radiation rate can be characterized as the quality factor of radiation, and the ohmic loss due to metal absorption can be characterized by the quality factor due to this ohmic loss. And the efficiency is simply the ratio of the radiative rate versus the total loss rate, or it simply can be expressed as a ratio of the Q to Q radiation. So this gives us some ideas how to optimize these LEDs. We need low radiation Q, so we really need to have an efficient antenna that radiates readily. Potentially, we can have such devices with a 50% efficiency. So this is pretty comparable to the quantum efficiency of lasers. Several research groups have looked at these issues, and there are various structures, such as a quantum well coupled to uniform sheet of metals, and quantum well coupled to antennas, optical antennas, located on top. In the first case, the efficiency is not very good since the sheet of metal is not well-controlled antenna radiation. In the second case, the coupling of quantum well active media to the antenna is not good enough. And more aggressive structures, you will place the emitter exactly in the feed gap of the antenna. This is difficult to do. Conceptual demonstration has been demonstrated in dye molecules. No semiconductor LED has been demonstrated. The last structure is what we are pursuing by placing the gate media in what we call arch dipole antenna structures, where the emission can be coupled more strongly to the antenna, and we can make the structure also very, very thin. And the fabrication process is summarized here. The cross-sectional picture. Essentially, we use a wafer bonding, flip the 3-5 wafers, perform electron beam lithography twice to make the structure. We define a nano-ridge of the active materials, which is indium gallium arsenide phosphide, for emission around 1550 nanometer wavelengths. And the antenna is in the orthogonal direction. So every cross in this picture represents a nano LED. For people in the electronic device area, you probably noted that this device looks very much like FinFET, and indeed, it is almost exactly like a FinFET, except the gate area is now replaced by antenna. It's metal oxide semiconductor structures, and we eventually, ideally, would like to have PIN doping rather than NIN or PIP for MOS. And a preliminary experimental demonstration show very promising results. I'll just direct you to the lower half of the comparison, where we measure light emission from these optical antennas to a control sample that have the same rich structure for the active material, but no antennas. And if we measure light output in the direction of the antenna radiation, that is polarization parallel to the antenna, which is shown in the green curve here, compare with a control sample with radiation, which is shown by the blue curve here, we see tremendous enhancement here, up to about 60 times enhancement in the emission by the optical antenna. So this is very promising. Let me just touch upon the Nano Detector, where we performed the theoretical investigations. And again, shrinking the detector has benefits including higher bandwidth and better sensitivity, higher voltage that leads to lower power consumption in the amplifiers. Now, if we look at sort of a generic structure, a detector, let's assume it to be a cubic shape. The capacitance is roughly proportional to the linear dimension of such a structure, multiplied by the dielectric constant. So as we shrink down the detector size, we have all these performance benefits. Ultimately, we'll be limited by two fundamental physical effects. One is a diffraction limit. When it's becoming smaller than diffraction limit, it becomes difficult to couple light into the detector. And also, the absorption length is limited by the amount of absorption coefficient in the semiconductor. So here, again, we use the same idea using optical antenna, which is known to collect and concentrate electromagnetic energy. Now, instead of two RF receiver, we will be concentrate that onto an optical detector. And this will provide a very effective path for scaling down the nano detectors. If we look at the results that are reported currently by a few research groups, this includes an aperture antenna, dipole antenna, the so-called bullseye antenna, and some antenna made by nanowires. I'll direct your attention to this efficiency column. All of them have efficiency lower than 0.1%. So this is a worrisome sign that maybe we can concentrate light to such a small area, but fundamentally it's a lossy process. On the way there, we lose most of the light, which will be defeating the purpose of having a high-performance, more sensitive nano detector. So we look at these fundamental process. What should the efficiency be in such antenna-coupled nanophoto detectors? And again, this is a very similar analysis as the one we performed for the nano LED structures. There are actually two factors. One is coupling efficiency. Coupling efficiency can be simply expressed as the optical beam spot size compared with the effective capturing area of the antenna. And then we have two losses competing for photons. One is absorption in metals, and the other one is absorption by the detector. And it's simply represented by these ratios of Qs in these structures. So we'll just use an example to illustrate the process. So let's look at the most common antenna structure, dipole antenna. So for dipole antennas, if we put the germanium in between, the antenna actually have a very nice, it's a very efficient antenna, but emitting in the wrong direction. Most of the radiation go to the substrate side because we have higher dielectric constant in the substrate. As a result, the coupling efficiency is very poor, only 0.5% if we couple from the top side. The internal quantum efficiency, which is a competition of detector and metal, isn't too bad, but overall the efficiency is actually very low, 0.06%. Now, if we look at some alternative structure, which has a bottom reflector, we can direct all the radiation upwards. We can have decent coupling efficiency as well as a better internal efficiency. This shows that efficiency of 10% is achievable with a single detector. We can use an array essentially to increase the coupling efficiency to 100%. So overall, 50% efficiency is quite feasible with such a structure. So to summarize, I think the question we started asking ourselves whether it is possible to achieve quantum limited detection with fundamentally lowest energy. It appears to be feasible, and there is a path to get there. That is by scaling down both emitters and receivers down to the nanoscale. And we have some preliminary experimental results that shows this is a very promising path. The future work will be looking at how to integrate such nano devices with silicon photonics infrastructures. Okay, thank you for your attention. Output power levels
for the laser,
for the laser,
speckle laser.
For the lasers, it's very low currently, and so we don't have a quantity measure. We do, but I guess we haven't converted that to watts. We should do that conversion. But currently it's low, but low for a few reasons. That we don't have good output coupling structure, so the light is really emitting by a very wide divergence angle. We're capturing also just a small portion. So that's one of the things we need to engineer. But fundamentally, if we look at the fundamental physics, the quantum efficiency allowed for such a laser is the ratio of the Qs, which is quite feasible to obtain on the order of 10 to 50% quantum efficiency.